Okay, so we were able to use our wave theory of light, or let me just say our wave theory, which we developed in chapter 17. We applied it to the double slit experiment with light, and we were able to figure out the exact positions of the mins and the maxes, which is awesome. So now what we have to do is we're going to figure out the intensities, right? We want to actually figure out what the intensities are and the pattern, right? I mean, it's great that we figured out where the max mins are, but now we want to figure out exactly what the intensities are. Oh boy, for the entire curve, all right? This entire thing, we want to figure out the intensities. It's not going to be easy. Okay, so a little bit review. We had this a while ago. Intensity is defined to be the power over area. And you remember that? Like a laser has super high intensity because the beam doesn't spread out, right? Okay. And then we learned for a wave, we learned that the intensity is proportional to the wave amplitude squared. So we had that, I don't know, some chapter, right? So the intensity was proportional to the wave amplitude squared. Remember, we also talked about the intensity from a point source, and we said that the intensity for a point source was proportional to 1 over the distance away from the point source squared. But we're not talking about point sources now, right? We're talking about waves. So intensity proportional to amplitude squared. Okay, now this is a proportion sign, right? You know, we don't like proportion signs. Okay, so let's just say if we just have one source, okay, one source of waves, we're just going to say that the I, intensity, equals some constant times the amplitude squared. I mean, no kidding, right? I mean, this is the same thing as that, right? Because if it's proportional, that means you can just put an equal sign with a constant of proportionality. Okay, now, so that's great. Okay, whoopee! All right, one source. Okay, now we're not going to be very smart right now. All right, we're going to pretend that we completely forgot everything we've learned about wave interference. So so this is one source. So for two sources, if we completely forget everything we've learned, all right, we're going to say that I2 is just equal to 2 I1, right? I mean, sort of makes sense. Really doesn't, actually, all right? So, I mean, sorry to say this, but this is dumb, right? Come on. You don't just add, you don't just double it, because when you have two sources, come on, we have interference for two sources. So we know this is wrong, because it doesn't account for interference, okay? So we're not going to do this, right? We have to include the effects of interference. Oh boy. And you remember there was all those trig identities and all that work. Oh, that's life, sorry. So that's what we're going to do. So goodbye. All right. I mean, that's why we learned chapter 17 before we did this chapter, you know, because we had to learn about interference. Here we go again. How many times have we seen these equations, right? So we had this in chapter 17. Here we have two waves traveling the same direction, da-da-da-da-da. And they interfere, so we add the displacements and we get this. We went over that in gory detail. And this is a function of kx minus omega t, so it's a traveling wave. This is the amplitude, right? This is the amplitude. Okay, so we got to know what that amplitude is because of this, right? So the amplitude of this wave, right, which is the sum of these two waves. So the amplitude is 2a cosine delta phi divided by 2. All right, wonderful. Now, the intensity is proportional to this squared, right? Okay, so I'm going to be a really rotten person right now. So what we're going to do to figure out what I2 is the intensity for two sources, we're going to use this, and then we're going to do a whole bunch of math, which actually we're not going to do. All right? So I'm skipping a ton of steps, but all I can tell you is we're going to do this, we're going to square that, and a whole bunch of other stuff. All right? And the result is this: 4I1 cosine squared pi d over lambda L y. So I actually used to go through all the math, and it took like 10 minutes, and it was just sort of boring for people. So I decided to skip the math. If you want to see the math, look in the book. But all I can say, I mean, you know, we could do it. I mean, it's nothing new. It's just a lot of algebra. Okay? So, what's the amplitude here? It's 4I. No kidding, right? It's not going to be 2I. It's 4I, right? Because we have to include interference, okay? So that's the important thing. When you have two sources, the intensity is not 2I, I mean the amplitude is not 2I1, it's 4I1. And that's because of the interference. And if you want to see the math, let me know. I'll show you. All right. Now, okay, yeah, I already said that. Okay, so this is what you get for the answer. When you have two sources, this is the intensity of light at the screen after the light goes through both slits. All right? Now, look at that. This predicts that the amplitude is the same, right? As you go away from the central slit, the central line here, this predicts that the intensity is the same. Is that true? No! Oh, thanks. Okay, so this equation is only correct for this guy. We saw earlier that the intensity died off, right? So we still have work to do. Okay, so this is fine for that central max, but that's it, right? It's wrong for the other ones. Well, that's kind of a bummer. However, it's not a total waste. This equation also gives us the correct location of the light spots and the dark spots. So, okay, so what I'd like you all to do, please. So I want you to use this equation, and this is y, right? 0, And what I'd like you to do is use this equation and find the positions on the screen, so ym, where I2 is a max. So just use that equation and figure out for what values of y you get a max. Okay? So, and again, this is something you have to do. This is what you're going to be doing your homework and your exam, so you got to do it. Don't just watch me do it. Okay, so pause your video and figure it out. Okay, we are back. Oh, I forgot to show you that. See how that intensity sort of dies off? So again, the central one is correct, but this predicts all of them have this intensity. So this is only true for that central one. Okay, let's do what we were supposed to. Oops, sorry. Okay, so now let's do the problem. All right. So we want to find the positions where I2 is a max. Well, if this is a max, what's the maximum cosine? 1, right? Or, yeah. So it's squared, so it could be, plus or minus 1, right? Okay, so here we go. So cosine of the angle, which is pi dy over lambda L, that's an L, that could equal plus or minus 1, right? Because that's the maximum cosine. Okay, well, where does cosine equal plus or minus 1? At 0, at pi, at 2 pi, and so forth and so on. So therefore, this says that pi dy over lambda L equals 0, pi, 2 pi, 3 pi, blah, 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 right? Well, that's stupid to write it like that. So let's be a little bit more intelligent. So that means that pi dy over lambda L equals m pi. Where now m equals 0, 1, 2, blah, blah, blah. Okay, awesome. So solve for y, right? Let's put a little m here. A little m here. So just solve for y. So therefore, ym equals m. Okay, what happens to the pi's? Goodbye, pi. So ym equals m lambda L over d. Where have you seen that before? That's the equation we figured out a few minutes ago. Okay, yay! All right, so this is still an awesome equation, right? We just have to modify it for the intensities over. I mean, at least it gives us, you know, where the bright spots and the dark spots are, but it just doesn't give us the right value for the intensity. But it's still pretty good. All right, so now we gotta, okay, so like I said, you know, now we gotta figure out how come it sort of dies off. It gets darker and darker and darker as it moves away from the center. So we gotta figure that out now. And in order to learn about that, we have to learn about something called diffraction. Diffraction. Okay, so what is diffraction? It's just another word for interference, to be honest with you. So diffraction is just interference from combining many, many waves. So when there's a lot of waves, they use the term diffraction. All right? But it's more than that, okay? It's also what happens to the wave when it goes through a slit, how it bends, or spreads, I guess is a better word, all right? Or like when the wave spreads around an obstacle, okay? So I'm just going to show you a couple of examples. So here's a light beam going through this slit. You can see it spreads out, right? You can see a pattern. We used to call it an interference pattern. Now we're going to call it a diffraction pattern. Same thing, you know? So that's diffraction. Okay, here, look at that. So this is just light, right? So if somebody's holding, I don't know, a ball or something like that, and you can see these patterns, right? So those are diffraction patterns. Now this is really a neat one. So this is like one of those single, like a double-edged razor blade. Okay, so let's see. So this is a shadow. All right, actual shadow of a razor blade illuminated by monochromatic light. That means one wavelength of light, like a laser, from a point source. Okay, so look right here. See that arrow right there? Whatever. Just look at that arrow, all right? So right there, right? Yeah. Okay, then they blow it up, they expand it. So this arrow is the same as this arrow. And what do you notice? You notice a pattern, right? So basically the light is coming in and it's going around this razor blade and it's creating this diffraction pattern. So that's what I mean. Diffraction is when it goes through a slit or when it goes around something. You see this pattern. Now, believe it or not, you can actually do it yourself. Some people have a really hard time with it. Some people do it immediately. I don't know what to say. But anyway, just take two fingers, or your thumb and your finger here, and put it super close to one another, but not touching. And then look up at a light. You should be able to see a diffraction pattern. So try it. You should be able to see it. All right, now, when we talked about the double slit experiment, we didn't discuss the slit width, right? The distance between the slits. We kind of ignored it. I mean, you know, we said it was there and we had it in our equation, but we didn't really, we ignored it, right? I mean, come on, think about it. Here, what's happening? When light is going through a slit, it bends. Well, we didn't talk about that when we did our double slit experiment, right? So now, you know, we got to talk about it, right? We got to talk about this crazy thing. Okay, so let's do it. All right. Now, what we're going to learn, or see, I guess, diffraction depends on the slit, well, on the wavelength, and also on the width of the opening. And I'm sorry, we're going to use A for that. That's what Randy Knight uses, all right? Okay? So the diffraction, how much it spreads, depends on the wavelength and as well as the width opening. So two things, right? Wavelength and width of the opening. Now, if we were in K 132, I would do the following demonstration. Well, hold it, sorry. Okay, first of all, here's a fact. So the wavelength of sound, well, you probably already know this, right? The wavelength of sound is much, much larger than the wavelength of light. That shouldn't be a surprise, right? So this is what I would do if we were in K 132. So just pretend I'm at the whiteboard, right? And there's a door there next to the sidewalk. So I would step outside the room. Let's just say I'm outside the room, and let's say that's the door. So I would stand outside the room, and I would stand by the wall, so nobody could see me, right? Then what I would do, I would talk. Okay, then I would say to everybody, "Can you hear me?" And of course, everybody would say, "Yes." All right. Then I would say, "Can you see my face?" And everybody would say, "No." So, what does that say about the diffraction of? What does that say about the diffraction of a wave? You can hear me, but you can't see me, right? So, in other words, the light waves didn't seem to spread out, because if they would have spread out, you could have seen me. But the sound waves certainly spread out. All right, so that means that the diffraction is proportional to the wavelength, right? The greater the wavelength, the more spreading, okay? Now, let's think about the width. The width of the slit. Okay, so here it's kind of a wide slit. Do you see much spreading? Nah, not much at all. Here is a really narrow slit, and you see how it spreads? Yeah. Okay, so what does it say? What does that imply? The narrower the slit, the bigger the diffraction. So that's one of those inverse relationships, right? So that means that the diffraction is proportional to 1 over A. Okay? All right, so basically then, what can we say? Just put these two together, right? We'll say that diffraction is proportional to lambda over A. So the bigger the wavelength, the more the diffraction, the smaller the slit width, the bigger the diffraction. And again, here's why Newton never saw diffraction, right? Because they never had anything, well, I mean, they didn't have lasers, right? So they didn't have a source with just one wavelength. The light is a combination of many colors, many wavelengths, so it's kind of hard to do something with many wavelengths. And then they didn't have something that had a really, really small width like we do. So they couldn't see the diffraction, all right? Okay, now, what we're going to use in the real world is something called the diffraction grating. Okay, so yeah, I just said that. We'll use that again, by the way. So this is called a diffraction grating. So rather than having just like 1 or 2 or 3 slits, so this is transparent, 600 slits or lines per millimeter. Now that's impressive, don't you think? I mean, it doesn't look like that, but 600 lines per millimeter, You can buy them where there's thousands of lines per millimeter. So that's a diffraction grating, okay? Pretty impressive. All right, so we gotta analyze a diffraction grating now. Okay, so here we have a diffraction grating, right, with a whole bunch of slits, and we're going to use pretty much the same logic as we used with the double slit experiment. We're going to say, pretty much parallel rays. The interference is caused by the different path lengths, very, very similar. And skipping all the math, I will show you the result. Oh, it's right there. So skipping all the math, here's the result. So the bright fringes are found where the D, right, here's D. So D is from one slit to the next slit, okay? So the bright fringes are found when D sine theta equals m lambda. Okay, well, where have you seen that before? Same equation, right? This is for the double slit, right? Okay, so there you go. We're not done yet, hold on. So here's the question for you. So here's a white light. I just answered this a couple minutes ago if you were paying attention. So here's a white light source passing through a diffraction grating, and you can see it you form the rainbows, right? So why does the white light spread out like this after passing through a diffraction grating? Well, again, sine theta is proportional to wavelength, right? Is that right up there, right? Sine theta is proportional to wavelength. Well, what's white light? White light is a combination of many different colored light, and that means different wavelengths. So that means that they're going to spread out, right? Because the larger the wavelength, the larger the sine of theta. Okay? So white light has many different wavelengths, so it's going to spread out when it passes through a diffraction grating. Okay, so if we were in class right now, I would hand out diffraction gratings, and I would have you take your diffraction gratings and look at the lights from the ceiling and look at the lights coming out of your cell phone, and you'd all be very impressed. But we can't do that, sorry. But I have a nice slide for you, though. So this is pretty cool. All right, so this is a light bulb, a funny shaped light bulb, right? And it's emitting only one wavelength of light, and so we have this light bulb, right? And then we're looking at that light bulb through a diffraction grating. And what do you see? You see different wavelengths of light being spread out. Okay, so that's what you see. So it's pretty cool. All right, pretty cool. All right, let's do this again. Let's calculate Ym. Well, y equals L tan theta. That should not be a surprise, right? So there you go. All right. Now, wait a minute though. Earlier, when we did this for double slit, I said tangent theta equals sine theta, right? I used the small angle approximation, but here, these are not small angles anymore. Okay, so that's what I mean. With a small angle approximation, you're going to be really careful. You can only use it when the angles are small. And when you do a diffraction grating, the angles are not small. They may be if you're just up here. If you're down here, they're not small. So we're just going to stick with this. Ym equals L tan theta. Okay, let's go back. All right, so if we have one slit, we're going to say that the maximum intensity is I1. And what did we learn if we have two slits? The maximum intensity is 4I1. So just guess. What do you think the maximum intensity would be if we had three slits? Just guess. 9I1. 4, 16. How about n? It would be n squared I1. Okay? I hope that makes some sense. All right. But, there is something called conservation of energy, right? So as you have more and more slits, the fringes, they get really narrow and narrow and narrow. They get narrower, All right, so we actually use these diffraction gratings to measure the wavelength of light. That's called spectroscopy. Astronomers use this all the time. They use a spectrograph to measure the wavelengths of light coming from stars and galaxies and whatever else, and they're actually able to identify elements in the star's atmosphere and so forth and so on. All right, this is a demonstration that I do every semester when I'm teaching this class in McKay 132. And so here, this is the front whiteboard. And this is in the back of the room. You know, this is where the physics equipment closet is. And so what I do, I take my little laser pointer and so I take my little laser pointer, just pretend this is diffraction grating. I have a 600 lines per millimeter diffraction grating. So that I just shine the light through the diffraction grating. So this is what happens. I shine it, right? And the diffraction grating, you know, spreads out the wave, right? Spreads out the light. And so I see one max here, and then I see another max here. So let's call this m equals 0 max, m equals 1 max. So then I ask a student to count the number of tiles from here to here, and then we just, you know, we know that the length of it, what the length of a tile is, and so we get a pretty good approximation of this. We're not being super careful, you know. I mean, I'm not standing exactly over the crack of a tile. I'm just kind of standing wherever. So we sort of approximate this as best we can. And then we have another couple students measure from here to here, you know, using a tape measure. Again, you know, we're not being super exact because, I mean, when I'm doing this, I can't hold it perfectly still. I'm sorry. And so, you know, so these maxes, you know, they're kind of moving around a little bit and they're kind of moving around, but we do our best, you know, but we don't lose any sleep over it. Okay, so this is what we do. All right, so we use a laser, and the laser has wavelength equal to 532 nanometers. Okay, now the equation, which I just showed you, is m lambda equals d sine theta, right? Okay, now for us, we just have m equals 1, makes it easy, right? And sine of theta is just opposite over hypotenuse, so it's just y over r. And again, we measure y and we measure x, then we just figure out what r is from the Pythagorean theorem. Okay, then we're going to get d. Okay, so look at this is 600 lines per millimeter, right? So we